Hello and welcome to the lecture on the analysis of quicksort. In the last lecture, we have seen how a quicksort works. The major function in a quicksort is of partitioning. So if we are able to do partition in a certain way, that affects the best case, worst case and average case complexity of a quicksort. Now let's see how it affects the complexities. Now as we know that in a quicksort, the real work happens during the divide step, which is the partitioning of the subarray. Okay, when you select the pivot and when it reaches its correct position, the array on the left hand side is less than or equal to it, and the array on the right hand side is greater than or equal to it. Okay, now let's see uh, what the partition can how the partition can affect the complexity of a quicksort. Now let's see how we get the best case complexity of a quicksort. Suppose you have an array of size n. You have an array of size n. Okay, in each step you are doing partition in such a way that the other part, this left hand part, is lump sum equal to n by 2 and the right hand part is also equal to n by 2. In the next step also you are doing the partition in such a way that the problem is divided into half of its previous size. Okay, we are dividing the problem in half. Similarly, you will reach a position where you will get a problem of size 1. So on this level you are doing a work of Cn. On this level again Cn. On this level n by 4 plus n by 4 plus n by 4 plus n by 4, which will be Cn. On the last level also Cn. Now if you can see, this is a binary tree. Okay, and the height of a binary tree is log n. So you are doing Cn work on each level till log n. So when you add this, you will get a complexity of order of n log n, and this complexity is equivalent to the merge sort complexity. Okay, in merge sort also you divide the array by half. So in a quicksort, if you do the partition in which you are getting the division from mid, then the complexity will be same as that of a merge sort. Now let's analyze the worst case complexity of a quicksort. Now let us suppose I have an array such that the elements in the array are 5, 4, 3, 2, 1. Now if I run the partitioning algorithm on this, then after the first iteration, see, since 5 is not less than equal to 1, neither 4 nor 3 nor 2, so no exchange will take place. At the end this 5 will be exchanged with this. Okay, so you will reach here 1, 4, 3, 2 and 5. So this was your pivot. You are not getting any array on the left hand side. This n minus 1 length of the array remains on the right hand side. Okay, now in the next step you will take this as the pivot element and it will not be swapped because 5 is at its correct position, but the partitioning algorithm will run. So if you have a problem of size n and you are not getting any problem on the left hand side to solve, and n minus 1 problems remain on the right hand side. Similarly, in the next step you are not getting any problem and the problem of size n minus 2 remains on the right hand side because you are not getting 5 displayed from its position, and the problem size n by 2 will remain because you will get 1, 4, 3, 2, 5. You have this problem to solve now. You will select 2 as the pivot and you will bring it here, 4 will go here. Okay, then similarly you are getting no problem to solve on the left hand side, but n minus 3 problems on the right hand side. Similarly, it will go up to 1. So you are solving the problem of size Cn on the first level, problem of size Cn minus 1 on the second level, problem of size Cn minus 2 on the third level, Cn minus 3 on the next level. Similarly, when you add it up, you will get Cn plus n minus 1 plus n minus 2 plus n minus 3 till this one. So this is sum of n natural numbers. Okay, and the complexity to add sum of n natural numbers is order of n square. So the worst case complexity of a quicksort is order of n square, and it will occur when you're getting a partition such that none of the array is on the left hand side and rest n minus 1 array is on the right hand side. Similarly, on each step you are getting a problem of size 0 on the first step and getting a problem of size remaining, that is n minus 1 or n minus k on the right hand side. So in this case, the worst case of quicksort will occur, which is order of n square. Now let's see how to analyze average case complexity of a quicksort. See, what you are doing, you have a problem of size of t of n. You are dividing the problem into two sizes, that is t of k and t of n minus k minus 1. Okay, this is your problem on the left hand side, say, and this is your problem on the right hand side, and you are doing partition, which is going to take theta of n times. So this is your general relation for the recurrence of a quicksort. If you are not getting any problem in size t of k, then your recurrence becomes t of 0 plus t of n minus 1 plus theta of n, which turns out to be order of n square, which is the worst case of a quicksort. And if you are getting a problem of half of the size, that is t of n by 2 and t of n by 2 plus theta of n, so it becomes 2t of n by 2 plus theta of n, and the solution is theta of n log n, which is similar to a merge sort, and this is the best case complexity of a quicksort. Okay, now let's analyze by varying this k the average case complexity of a quicksort. Now let us say I am doing partition such that I am getting 1 by 4th of the problem on the left hand side and remaining 3/4 problem on the right hand side. That is, my t of n is going to give me t of n by 4 on the left hand side and t of 3n by 4 on the right hand side, and this is your partitioning complexity. So this is your recurrence in this case. So what will be the complexity here? See, you are getting n by 4 problems on the left hand side. When you further divide it, it will be n by 16, 1 by 4th of n by 4 on the left hand side and 3n by 4 on the right hand side, which is 3n by 16. Similarly here, you will get it 3n by 16 and 9n by 16. Similarly, this tree will go till you reach a problem of size n1. Now see, the problem on the left hand side is smaller. So this branch will be exhausted easily, more quickly as compared to the right hand side branch. So the depth of the right hand side branch will be more as compared to the depth of the left hand side branch. So the depth of the left hand side branch will be log n base 4, and the depth on the right hand side branch will be log n base 4 by 3. You are doing a work of Cn on the first level, Cn on the next level, till all the bases are equal, till you reach a level where the depth of the tree on left and right are equal. You are doing a work of C of n. After that, this left hand side is exhausted. You are only left with the right hand side. So the work done will be less than C of n on each of the level. So when you add it, it will be order of n log n. You can also solve this recurrence to reach this. conclusion. Okay. Now let's see if we get a split of 1:9. What happens in that case? So now we are getting a split of 1:9. Suppose I had a problem of size n. Now on the left hand side I am getting 1/9th part, that is n by 10, and on the right hand side I am getting the remaining parts, that is 9n by 10. Similarly, on the next step I am going to get n by 10 and 1 by 10, n by 10 and 9 by 10, 9n by 10 and 1 by 10, 9n by 10 and 1 by 10. Similarly, I will reach 1 and 1. I will reach a position where the size of the problem will remain only 1. See, again, here the size of the problem is only n by 10, and here the size of the problem is 9n by 10. So this part will be exhausted quickly as compared to this part. So the depth of the right hand side of the tree will be more, and it will be log n 10 base 9, and this will be log n base 10. Okay. So when you try to analyze it, the recurrence will be T of n is equal to T of n by 10 plus T of 9n by 10 plus theta of n. And when you solve this recurrence, you are going to get a relation or the time complexity as order of n log n. So if you are getting a split of even 1:9 or 1:99 or 1:999, or you are getting a split such that on one of the level you are getting the best case, which is n by 2, and one level you are getting the worst case, okay, which is 0 is to t of n minus 1, 0 is to n minus 1. If you are getting a complexity of best case on one level and worst case on another level, then also your complexity is going to be order of n log n. So now you can see that the complexity depends on how you select the pivot element. Okay, so such that you do not fall in the trap of the worst case, we have a randomized way to select the pivot element. Now let's see how we select the pivot randomly. Now let's see how to select pivot randomly. You are calling a function randomized partition on the array A with the initial index as P and the last index as R. Now you are calling a random function to select any number from index P to R, and you are storing that it in the variable I. Okay, suppose you have the array, you are calling a random function, suppose it selects the second element. Now what you do, you exchange it with the last element. Okay, suppose your last element was A of R and this was your I, you exchange this. Now you return and call the partition on this array A from P to R. Now you have exchanged this this element with the last element, so that the trap in which you could fall such that this T of n is equal to T of 0 plus T of n minus 1 plus theta of n. By the rule of probability, it is very less that you will fall in this trap when you are selecting pivot element randomly each time. Okay, so that's why we do random partition, such that we could reach the complexity of order of n log n instead of order of n square. Now let's write randomized quicksort algorithm. So in the randomized quicksort algorithm, you are calling a function randomized quicksort on the array A from P to R. P is the starting index, R is the last index. So if start is less than R, you are calling randomized partition. As you see in the last slide, how we call randomized partition, you select any element, swap it with the last element, and you call the partitioning algorithm. Okay, you assign it in the variable q, and then you call randomized quicksort on the left hand side of the partition, that is from on the array A from P till that partition, and randomized quicksort on the right hand side from q plus 1 from the next element of the partition till the end of the array. So in this way, you can do randomized quicksort. Okay. So today we have learned the best, worst, and average case complexity of a quicksort, and how randomized selection of pivot element can help us in getting that average case complexity of a quicksort. Okay. Now let's see you in another lecture. Thank you.